Okay, so velocity. A lot of people think of velocity and speed as the same thing, but they're not quite the same because velocity is a vector quantity, which means that it includes direction. Speed is scalar and does not include direction. So instead of being the distance, velocity is the displacement of an object. In a unit of time. Since displacement includes direction, so does velocity. The formula looks very similar to the speed formula, except instead of distance, we're going to put displacement. Velocity is displacement over the change in time. So our units are going to look very similar to our our speed units, except that they're going to have a direction with them. So we could have a negative some number of meters per second, or we could have a positive number of miles per hour. Or we could say meters per second north, or miles per hour left, or kilometers per hour east, or centimeters per day up. Okay, we need a unit that tells us distance over time, what distance and time units are we using, and then we need some sort of direction. It can be a positive or negative direction, or it can be a north, east, south, west direction, a left, right direction, a forward, backwards direction, or an up, down direction. All of these are directions, acceptable directions. All right, let's look at what a vector actually is. A vector is a picture. It's like a diagram or a picture of a quantity. The size of the, it's always drawn with arrows. This diagram is always drawn with arrows. The size of the arrow tells us the magnitude of the quantity. The direction of the arrow tells us the direction of the quantity. Okay, so if we have a really big arrow, that means we've got a really big magnitude, which is the number part. If it's in a positive direction, then we have a positive quantity. If we have a little arrow, then we have a small magnitude. If it's going in the opposite, in a negative direction, then it's a negative quantity. So here we've got two vectors drawn for two different ants. This little ant's going to the left, that's negative, and it's going 2 centimeters per second. This little ant is going the same velocity, so it has the same size arrow, but it's going in a different direction. So the arrow points in a different direction, and we've got a positive 2 centimeters per second. When you look at vectors, if you see the vector for this little car up here at the top, it's always the same size and the same direction. So that tells us that our velocity is not changing. Which means that it's a constant velocity. Down here we've got this little car, and as we move along, these vectors are getting longer and longer. So that tells me that our speed is getting greater and greater, but our direction is always going forward. Our forward direction doesn't change. So that tells me that we're getting faster, but our direction is staying the same. So that tells me that my velocity is changing. We can change velocity in two ways. We can do it by changing the speed or changing the direction. Vectors are very useful in science and in other applications. For example, here we've got this little Mars rover. This little guy is like a robot, was sent up to Mars in 1997. And he's been up there ever since. He takes soil samples and atmospheric samples and rock samples and does all sort of kind of chemical tests on them to determine what's up there. He takes pictures, and the scientists back here on Earth figure out where he is using vectors. Let's look at an example. Here, the Mars rover told the scientists that it went 2 meters per second forward, so that's a positive direction, for 10 seconds. So if you take where the little guy started, here's where he started. If you want to figure out where he is now, right, then we can say, well, we use our velocity displacement over change in time. He said that his velocity was a positive, positive 0.2 meters per second. Displacement we don't know, but we know change in time was 10 seconds. So we can plug in a positive 0.2 meters per second, displacement over 10 seconds. We can solve by algebra or by cross multiplying, and we get 10 seconds times positive 0.2 meters per second is displacement. So our displacement is positive 10 seconds cancel meters from where we started. So if we were going forward or east, then maybe that would be east, or forward. It's probably a northeast, southwest sort of direction, but might not be. It might use a different direction. Let's look at this one. You could also say, no, now I'm going a negative 0.2. Right now my velocity is negative 0.2 meters per second. My time is now 4 seconds. So where am I now from where I started? Let's plug in. Okay, again, we can solve by cross multiplying or by using algebra. 4 seconds times negative 0.2 meters per second gives me my displacement. Seconds cancel. 4 times negative 0.2 is negative 0.8 meters. And so that's my displacement. We can use this for people walking around, cars, buses, other kind of things that we want to keep track of. The thing is that if you change directions, you're going to need to calculate your displacement for each separate leg. So this would be like part 1 of your motion, motion 1, and here would be movement 2, or motion 2. Okay, so for 1, I'm going east, that's my direction, for 10 seconds, that's change in time, at a speed of 2 meters per second. So my velocity is 2 meters per second east. My displacement I don't know, but my change in time I know is 10 seconds. So plug in. Two meters per second, east, is displacement over change in time, which is 10 seconds. 10 seconds times 2 meters per second east is my distance. Seconds cancel and I get 20 meters east is my displacement. So on this first journey of my part of my journey, first leg of my journey, I went 20 meters east. Then I made a turn and I went south at the same speed, so my speed is still 2 meters per second, 10 more seconds. So there's my change in time. So for my second leg, My velocity now is 2 meters per second south. My displacement, I don't know, but my change in time is another 10 seconds. So my second velocity, displacement over change in time. I know my second velocity was 2 meters per second south. Distance I don't know, change in time is 10 seconds. So I can solve by algebra or by cross multiplying, and I get 10 seconds times 2 meters per second, south, gives me my displacement. So now I'm 20 meters south of where I started. So my final position is 20 meters east and 20 meters south of my initial position. Okay? You can kind of think of it like on a coordinate plane, right? Where if this is where I started at 0, 0, here I went 20 meters, and then here I went another 20 meters, right? So my ending point would be at this point right here, sort of positive 20 meters, negative 20 meters, right? If this is my ending point, see, I'm at this point. Right there where those two lines intersect. So that's positive 20 intersecting with negative 20, right? Okay, let's look at some example problems. Let's just look at one. Let's say a car travels 30 kilometers, if they're in a car, 30 kilometers west at a speed or velocity of 5 kilometers per minute west. How long did it take? Well, I know I'm going to use the formula velocity, displacement over change in time. My velocity is 5 kilometers per minute west. It's a very fast moving car. My distance is 30, or my displacement rather, kilometers west. And my change in time, that's what I'm looking for. So I can plug in 5 kilometers per minute west is equal to 30 kilometers, kilometers, west over change in time. To solve this, I can do the same thing, cross multiply or use algebra, and I get change in time times 5 kilometers per minute west equals 30 kilometers west. I need to divide both sides by 5 kilometers west. Right, so I can cancel this out and just be left with time over here. So my change in time is going to be 30 divided by 5 is 6. My kilometers west cancels. I'm left with 6 minutes. That's how long it took me to go those 30 kilometers if I was going at a velocity of 5 kilometers per minute.